Yep. So I'm Luis. I work with BrainBot as a product manager on Shutter, and especially as Philippe said, today we're talking about this sort of three-way collaboration between Gnosis team and Nethermind team and Shutter, and it's about we call it the Shutterized beacon chain, kind of as implemented on Gnosis chain, which means it is an encrypted mempool using threshold encryption. To protect against front running and malicious MEV and real-time censorship, make it basically a more base layer neutral and more decentralized chain. And the way we'll start is, the important part also maybe top down is tomorrow it'll go live essentially. So we already have some validators even running it. So you guys will be able to get a sneak peek, maybe even to try it out. Maybe it'll break. It's a little bit of a sort of like a thing with a lot of moving parts, but yeah. Teaser to what is coming next. Official launch tomorrow. So, Shutter is we think is actually more than just this one sort of technology. It's more about kind of the promotion of base layer neutrality, information symmetry, accessibility, and the core technology we're using essentially is this commit and reveal gadget using threshold encryption. So it's encryption technology, but it's not necessarily like aimed at privacy or anonymity, but rather to serve as a commit real gadget to have some parties, any party in different use cases, commit to something and then only reveal once the information level of everyone is sort of the same level. Only then do we reveal and sort of like execute, for example. So one of them is the trading, where it's very important that everyone has the same information level when they trade. Another one is voting. So we have a integration with Snapshot, where it encrypts the voting results during the duration of the vote. And there again, it's about information symmetry, because if you have public voting results during the vote, people who vote later have more information than other people. I think it's like a nice connection to the first talk where we talked about like distribution of information in circles, right? And this is it's very important that we have to have information symmetry, or the more information symmetry, the more efficient and the more accessible we think systems are. Yeah, gaming is another use case. But let's play a game. This will sort of display what front running is and why it's important to combat it essentially. And we'll play this game, and we'll have Loring and Philippe play the rock, paper, scissors game.
Okay, so does everyone know how to play rock, paper, scissors? No. It's an extremely complicated game. The rules are you can show rock, paper, or scissors, and you have to do so on the count of 3. So, Philip, let's get started with a demo game. Are you ready?
I am.
1, 2, 3. And we have an instant rematch. Let's go again. 1, 2, 3. 1, 2, 3. Okay, and I won. So this actually works pretty well because we're playing a low-stakes game, and we generally trust each other, and both of us have basically the same reflexes, meaning that we both show at the same time. Neither one of us has an advantage. Neither one of us can see the other player's move before we decide our own move. But let's change this up a little bit, and let's introduce information asymmetry into the game. So the new rules are, Philip is going to show his hand, and then I'm going to take a look at it, and I'm going to show my hand. Sounds wonderful, doesn't it? Okay, let's get started. You ready?
I am.
1, 2, 3. And I won! This may be an anomaly, so let's play again. 1, 2, 3. Oh, okay, and I win again. So I'm going to win every single time when I have the advantage of information asymmetry. When I can see my opponent's move and then I can respond accordingly. I win every single time. And it's a fucking stupid game. No one would ever play this game, right? But we play this game every single day on chain. When you send a transaction to an unencrypted mempool, you're basically revealing your move first, and then attackers are able to see your move and respond accordingly. And guess what? You lose every single time. Handing it back over to Lewis.
Thanks. Yeah, I think it makes it awesome, actually very transparent what it's about, right? Information symmetry or asymmetry. And then let's go one level sort of deeper, right? How it manifests on chain is we call it MEV, so maximal extractable value. And it's the amount of value you can extract due to sort of being able to unfairly reorder transactions or front-run transactions. And one of the basic ones is just your traditional sort of front-run, and then combining it with a back run, so it's a sandwich attack. So you front run someone, and then afterwards you exploit, you arbitrage him another time essentially. So how it works, sort of there's let's say a bigger order coming in, and someone sees that order and sees, let's say, a buy order, and is able to exploit that information that there is a large buy order coming in, buys right before, so that buy order will drive up the price, right? And the attacker can because they know that this transaction will come in, they can slot in right before, sort of jump the queue, buy the token beforehand, and then sell even more expensive to the victim. And then who actually benefits from this is sort of like pretty asymmetric, and it's not everyone has the same access. It's like we have this complex transaction supply chain. More on this later, but here's just an example of like a bigger sandwich attack. So this was actually when the Ethereum Foundation wanted to offload some ETH. I think it was a larger trade, and they were sandwiched, right, by someone. And this is how it looks like. I don't want to get in detail how it worked. The actual sequence of how it works is 39 steps. So I won't be able to go into it. But very, very basically, the attacker can essentially, this is a classic one. So they borrow some wrapped ETH somewhere, swap it, raise the USDC price, and then the victim, the Ethereum Foundation in this case, had this problem of this higher manipulated price on the Uniswap V3 pool, and then the attacker borrows another time sort of a lot of ETH to arbitrage and then repay the flash loan and then collects back the revenue. Yeah, and it's sort of a lot of steps in between. Just a summary of this, and it creates just losses, right? It just creates a lot of measurable losses for many people. Depends a little bit on bull market or bear market, but essentially it's probably in the hundreds of millions of dollars per year. And then we also think sort of the one thing is that the measurable amount of front running, but even harder to measure, but potentially even worse, or equally worse at least, is sort of UX issues, right? Because if you get front run, your transaction might fail as well. And then just the combination of loss of trust. So, this is something that people know about, right? Or that gets through to let's say serious investors or mainstream, and they see this and they see that it seems to be an extremely intransparent and unfair game. So some of these serious or mainstream investors are even staying away from DeFi because of shenanigans like this, essentially. And then we have another interesting one. So, for example, MiCA, this regulatory regime in the EU for crypto, they recently mentioned MEV and mentioned sort of that ability to order transactions unfairly in a way, and are moving in to sort of like potentially regulate transaction supply chain intermediaries, or let's say validators or sequencers. And obviously, we would probably all agree is that's something that shouldn't be regulated, but the threat is there, and the more asymmetric power a validator or transaction supply chain intermediary has, the more there's the threat of being regulated. So we would argue we should fix it. We should fix it before it gets regulated, essentially, instead of it having to be regulated. And this all also really connects to censorship. So I would say in general we have a high level of censorship resistance on Ethereum and Gnosis chain because of the decentralization of the validator set. But it's not the case for like a smaller time scale. And this is what we would call a real-time censorship. And this actually matters a lot as well. It depends on the urgency of a transaction, but sort of like below a certain time scale, censorship is possible and is being done, right? And we think this is also extremely important to fix ideally. And just the larger point of nobody cares, you don't need censorship resistance until sometimes suddenly you do, because let's say you are sort of persecuted, or you did something bad or something, or we're unlucky, suddenly you need censorship resistance. I think that's why we're all in blockchain. And it's happening, it's actually happening like in practice, right? This is more the larger scale of sort of OFAC list censoring here. They came out with the Tornado Cash stuff, but the amount of validator censorship has actually gone down. So there's actually less validator censoring. But what's less talked about is relay and builder censorship. So for those who don't really know, so this is sort of the modern PBS transaction supply chain. So as a user in the past or Gnosis chain, you send it directly to the validator or via RPC to validator, and it's sort of like simple-ish how the transaction moves. In Ethereum now, mainnet, you have this PBS transaction supply chain where builders are building blocks, and then via relays they're sending it to proposers, and they enter it into the block. And in theory, those are all sort of points of failure, or not points of failure, but essentially transaction supply chain intermediaries that can all potentially front run or censor. So that's what makes it sort of problematic, that you have this complicated transaction supply chain and you have centralization at some of these levels. Like there's not a lot of relays, for example. And just on the higher level, we think is sort of having more baseline neutrality, for example, via decentralization or via encryption, let's say mempool encryption. We think we can achieve a more level playing field for everyone. And this is how it connects, we think, to accessibility, because the more level the playing field is, the more everyone can sort of participate at the same information level and same level of access. And we think that's how it connects to this event as well, the user agency, right? Because the more power you have using via encryption, the more user agency you have, and the more so and hand over to Yannick now for the actual what we're doing actually. Yeah. So this was all just the preamble. So Yannick will.
Yes. So I'm basically going to talk about what we're building in practice, and that's as Louis already mentioned, like this encrypted mempool. So we allow users to encrypt their transactions so that when they send it to the network, no one else can see it. Not even the block proposer or the builder that eventually includes it in the block. So they have to build the block without knowing what the transactions do. And that does not prevent censorship or front running, but it makes it basically ineffective, because if you don't know what transactions do, you can't do it in any meaningful way. So for example, if for front running, you would need to know if a transaction is a buy order or a sell order, but if it's encrypted, it could be either of those. So when we have now these encrypted transactions in a block, that doesn't help us a lot. We need to, in order to execute them, we need to decrypt them so that the network can execute them, that we know the post state afterwards. And there's different ways to do it, a few different ways. Kind of the naive way would be to ask the user to do that. The user encrypts locally using a key that they chose, and then when the transaction is included, they later publish the key for that to do the decryption. Now this would be very ugly, because it's very bad UX. You have to do two things in order to, you have to send two messages in order to do one thing. And also, it would break like a lot of crypto protocols or smart contracts, because now the user has all of a sudden the option of not decrypting at all. Like if it turns out that they don't like the outcome that that the transaction would have, they can just go away, not send the key, and the protocol would have to find a way to deal with that, and that's quite complicated. So what we do instead, we do threshold decryption, which means we have a committee of nodes. We call it the keepers. And they collectively produce encryption keys and decryption keys that users then can use. And they do this at the right point in time. So they only produce the decryption keys when a transaction has already been included and the order cannot be changed anymore. And this relies on an honesty assumption. So as long as we can assume that the majority of these nodes is honest, then the protocol works as expected. It's kind of the basic principle. I now want to go a little bit into the concrete implementation, into the details. And if you instantiate such a protocol, you of course have to make some concrete decisions, and those are guided by principles or basically the goals you have with your protocol. And the goals we had were first of all minimize risks. So we're working here with Gnosis chain, which is a live network, and it is very useful for people. And now if we change things in the protocol, we don't want to risk breaking it. So we try to roll it out in a way that it starts very small, and if for some reason things don't work, at least the maybe Shutter doesn't work, but the chain itself continues working. So most importantly, we can't do a hard fork, or we don't want to do a hard fork to do this, at least not in the very beginning. We also want to have very little UX impact, so users ideally shouldn't even notice that they use Shutter. It should all happen in the background. Of course, we want the protocol to be secure, but in the very beginning, we are willing to sacrifice perfect security if it kind of collides with the other goals we have. But that's only temporary. Long term, we want to be able to iterate over the protocol and improve it over time to get rid of these these initial security problems. All right, so now we can go step by step through the protocol, how it works. And it starts, it uses a lot of smart contracts. Smart contracts are always yellow in these slides. And it starts by the keeper set manager contract. That's basically a contract that tells everyone who the members of this committee are, who are the entities that are allowed to produce these keys. And it's restricted, so not everyone can simply register, but we have the Shutter DAO that selects kind of these keepers. And that's kind of important because the goal of the Shutter DAO, the purpose is to make sure that it selects nodes that can be trusted and are honest and are not at risk of colluding. So, for example, what we want the Shutter DAO to do is to select keepers that come from different backgrounds, so that they're not all from one company, for example, or they come from all over the world, ideally. Yeah, so from basically a diverse background. This you couldn't do it. You couldn't do something like this if you had similar to the validator set of Gnosis chain or Ethereum, where simply everyone can register. That works maybe if your set is very large, but for technical reasons that I will go into later, the set has to be somewhat smaller than that. All right. So now, if we have a new keeper set, the first thing they have to do is, of course, they have to start producing these keys. And you do this usually using a distributed key generation protocol, and they tend to be very inefficient. And they tend to have a quadratic communication overhead. So every one of these nodes has to send a message to all other nodes. And that makes it very slow, especially if we have a large size of this set. So but it's kind of fundamental, so I don't think there's a way to get around it. But the way to mitigate it that is in our protocol is we kind of contain this quadratic phase in only a setup phase. So only once when a new keeper set starts, they generate this key in advance. They do this key generation process once, and it outputs an encryption key that then everyone can use for encryption. But then for decryption, which has to happen at every single block, every one of these keeper nodes only has to send a single message. So that's kind of maximally efficient. You can't really get much better than that. Okay, now if we have this encryption key, now the users have to know this key in order to send transactions. So the keepers now broadcast it via a contract. Again, they could also broadcast it via a peer-to-peer network, but that's much more difficult for users to observe. Whereas a contract, everyone knows how to read a key from a contract. Okay, so that was kind of the encryption side. Now we have to go to the decryption side. And the decryption has to be done by the validators. So as I said in the beginning, we want to minimize risks. We don't want to change every single code on every single validator, because it could mean that if there's a bug, then maybe all of the validators go down. That wouldn't be good. So we want to roll this out slowly to more and more validators over time. And to do that, we have what we call the validator registry contract. So once a validator, in the beginning, it's empty, no one participates in the protocol. Once a validator feels confident in the protocol and wants to support it, they send a signed message to this registry contract. And over time, this registry will grow. And now the keepers will observe this registry at every point in time, and only produce keys for those blocks where there is a registered validator. So that's basically the way of the protocol to ensure that it won't break the whole network. It will, we will slowly ramp it up. The downside here, of course, is a little bit user experience issue. If you send a transaction in the very beginning, then it might take a long time until there's a registered validator to propose a block. So they have to live with a little bit of higher latency, but that's kind of a trade-off that we have to accept here. Okay, how does it look for the user? The user fetches this key from the key broadcast contract. It now encrypts that transaction and wraps it in another transaction and sends it to the sequencer contract. The sequencer contract is kind of is taking on this job of ordering the transactions, or putting them in some order, and makes it kind of publicly known what these transactions are. Then the keepers observe this contract, and then produce at every block keys for these transactions in the contract, and publish it on a peer-to-peer network. The proposers, or the proposer for this particular block, will watch the network, wait for the key, then fetch the transactions from the contract, decrypt them, and put them in the front of the block. And now there's still a lot of other transactions, other space in the block, and they can fill it with normal transactions that are from the public mempool. Question?
Sorry, I'm just going to make this interactive. Why is a proposer following the sequence here? Or maybe you get to this, but I just...
So, I mean, proposers are the entities that build the blocks, right? So if we want to get something into blocks...
but it's not forking the consensus layer, so is a proposer required to follow the sequence from this contract? And if not, or if yes?
Good question. Okay, important question. In the beginning, no. So ideally, it would be kind of the rules of the protocol. Maybe even the proposer wouldn't have to participate in this. The rules of the chain could execute the transactions automatically because they are already in the sequencer. But this would require a hard fork, and as I said, we don't want to do this to keep the risks very low in the beginning, and also to stay aligned with Ethereum, so that the rules of Gnosis chain are as similar as possible with Ethereum. We come to security assumptions there in a second, because right now there's also not really an enforcement of this. But yeah. Okay. Before we go into that, I said the user has to encrypt the transaction. Of course, this should happen automatically somehow. And ideally either in the front end of your application that you use, of the app that you use, or in the wallet. And that's kind of the two places where it would make sense. But in the beginning, it's unlikely that this gets a lot of support. And during this transition period, we kind of provide this, what we call the encrypting RPC server, which is a trusted entity for now, that you can just plug into, replace your normal RPC with this RPC. You send your plaintext transaction to it, and it will perform the decryption and sending it to the sequencer contract behind the scenes. So again, like a trade-off between UX impact and trust assumptions. Okay, yeah, and that's kind of the point you just raised. There's not any enforcement of these rules yet. They're kind of defined by the protocol, so I would say it's misbehaving, but no enforcement yet. And we have like a bunch of steps that we want to do in the future to make this more secure. And kind of the first easy step is to simply kick out nodes when we see that there's some misbehavior. And importantly, this is like is easy to check. Yeah, and how you could implement this, we are discussing a few things here. One would be like by vote of the validators. Another would be by vote of the keepers. And that's kind of the main two options here, I think. Next, we can slash proposers if they misbehave. So we can require them to put up a stake, or maybe we can use like something like eigenlayer to even slash their main Gnosis chain stake. That would also automatically kick them out. At some point, it would be nice to make participation mandatory as well, so that users can expect that every proposer will execute transactions. And lastly, if we can do a hard fork eventually, but that's like long term, then we can just make these blocks invalid if they don't follow these rules, and then the whole network will just reject them, and the next proposer would kind of replace them. So that's misbehavior of the validators. The keepers can also misbehave, and it's a bit more tricky here because it's much more difficult to prove misbehavior of the keepers. But we still have some ideas here. We're already working on a staking process. We can do social slashing, so we can do like observe the network and have like social rules how the keepers are supposed to behave and slash them if they don't. And also there's some fancy cryptographic protocols that are developed right now that even like where we can have some proof of collusion, but that's like quite complicated. Okay, yeah, that's all from me. I guess I hand it back to Louis.
Thank you. So just two more slides sort of on the just two more slides on sort of the practicality on how it's going, well, how it's launching essentially tomorrow. And again, this is a little sneak peek, and it's there's, I would say, some issues right now, some stability issues, and some transaction inclusion time issues. But yeah, in theory, we have these both of these different ways how to use it. One is, as Yannick mentioned, adding this specific encrypting RPC to, let's say, MetaMask or wherever you trade. And that's all you have to do, essentially. And then in the background, it is encrypting the transactions. And you are sort of implicitly benefiting from the encryption. And it's actually kind of like anticlimactic because it just sort of should just work like another transaction, and you're not actually necessarily seeing that it is encrypted. So yeah, and then these caveats currently have still quite a long time for the transaction to be included, because yeah, what Yannick mentioned, there's not a lot of validator yet to run this specialized Nethermind version. And we're currently in this onboarding phase, and we'll onboard more of them. It'll improve. And just in general, it's really like a beta feature still, right? It's a beta release, and there can be some problems about, for example, transactions getting lost. So tread very carefully for now. And then also something else very amazing is on the right there you see how it is natively integrated into a demo dApp in this case. And yeah, so there would not require the RPC, but rather kind of directly be integrate the encryption part into the front end, and then we have this more kind of end-to-end encryption, which is actually the desirable way to do it, right? And again, this will also launch hopefully tomorrow or sometimes some days afterwards, but this should already work essentially. Yeah. We have a bunch of, I would say, outreach or action items for interested parties, developers, and validators. So if you are a Gnosis chain validator, it would be super interesting for us to get in touch, and for you, if you're interested in this, to learn about it and sort of learn what the validator registration steps are, and how to get onboarded. And if you want, just join this Telegram group with a bunch of other Gnosis chain validators. And then for any wallet or dApp developer, especially on Gnosis chain, we would love to also get in touch in case you're interested in natively supporting the encryption on the front end, essentially. And then, and this connects to the second talk we had today about AI. So we have the ShutterDAO 0x36 has a grant available, sort of, or an RFP essentially, for any OLAS builders to work on essentially autonomous agents to stress test and simulate the encrypted mempool. So that's an opportunity to work on with the OLAS stack on Gnosis chain, on Shutter. I think it's a cool opportunity. And that's sort of it. Would be awesome if you could spread the word. We think it's a longer term thing, right? So it's about baseline neutrality, and it's about information symmetry. It's not so we need kind of people to talk about it, and we need people to essentially buy in, to run the validators, and to effectively commit to it. Would be awesome if you can spread the word and start trading on it, and encourage others to integrate Shutter essentially. Thank you. And we're not doing the sandwich tag, right? Yeah. This is. Thank you so much.
If you'd like to play a game of rock, paper, scissors, or if you would like to help bash a giant sandwich piñata, there's 1 day left to do so. We are celebrating the launch of Shutterized Gnosis chain directly outside the EthCC venue tomorrow afternoon from 2 to 5 p.m. So come by, take a swing at the piñata, and play rock, paper, scissors. You will lose.
And forgot something to say. Fred's talk will be at the main event tomorrow. What time again? Do we know? 1:25. Yeah, in the Silver Hall, right? Yeah. So and there he'll go into more detail, and that'll be the actual launch, sort of. Yeah. All right. Do we have any questions?
What is the sequencer contract and where is it?
On Gnosis chain.
If you already have the mempool encrypted, why do you need the contract?
So I'll give a high-level answer, but I think probably Yannick can elaborate. But essentially, that's a way to really separate the transaction ordering and make it explicit that we are giving up the control and finalizing the order of the transactions. But yeah, probably Yannick would probably have a better answer.
Also, it's going to be hard for the proposer to do it without actually validating the transaction is correct, as long as it's encrypted. And I would only order it after I know it's valid.
So about the encrypted mempool, that's kind of how we describe it, because that's how it's working conceptually. I'm not sure if what in practice in this implementation is the encrypted mempool. In some sense, we kind of piggyback on the existing public mempool by we send the encrypted transaction by wrapping it in a normal transaction and sending it through the normal mempool. So that's kind of the encrypted mempool in a way, or that part of it. Or we could say that the transactions in the sequencer contract are the encrypted mempool, but here the transactions are already ordered and kind of forced to be included, so also not kind of the mempool. So I don't think that's like an exact equivalent of the public mempool in the system, but yeah. And there was another question you just had about, what was it again? Sorry. Oh yes. So for the for the proposer in the end, it's very easy. If there's an invalid transaction, they just ignore it. Now there's a problem with spamming potentially. So you could, if you don't have to pay for this transaction, then you could spam a lot of these free transactions, and that's why we charge a fee when you submit the transaction to the sequencer contract already. And the address of the sequencer contract is in a GitHub repository. I can send it to you if you like.
Right. Yeah. Sorry, I beat you to the mic. I think you maybe partially answered the question already of like how, well, until you do the final step of hard forking and you can just adopt sort of the normal transaction fee model, even though there's probably complications there. Right now you need to first pay for submitting to the contract, and then as you said, and actually went into detail, you don't know what the cost of the encrypted transaction is yet. So but you've clearly, I thought you were just going to sponsor this upfront for now until you hard fork, but you maybe have put more work into this already with the fee on the contract.
So the encrypting RPC is currently sponsoring it, so they pay the fee. But that's not necessary for the system right now. So when you send an encrypted transaction, you also specify publicly the gas limit, and then you pay for that. So no, not at the moment. But I mean, that's also, I guess, one of the trade-offs we have. But fortunately, fees right now are like low enough so that I don't think it matters in practice.
Yeah. So the question was exactly about this, like the fee. There is an extra fee if you want to use the encrypted mempool, right?
Yes.
I guess in Gnosis 10 doesn't really matter much unless you do volume. How big is it right now?
The fee? That's just basically a factor of 2 essentially. So you pay the base fee at the inclusion time. So it might be a little bit more or less depending on how much the fee is in the end, but on average you pay a factor of 2 more.
Okay, thanks.
If we can change like the rules a little bit, then we could, conceptually we could get around it. Like we could refund fees that were paid to more than, if a user overpaid, we can refund a little bit, but yeah, that would require a hard fork.
I have 2 questions. So you're talking about the extra fee. So I guess that's how the validators get then rewarded for including the encrypted transactions, right? That's why the user paid more fees.
So right now we try to keep it very simple. We need the fee mostly for spam prevention. So right now we just burn the fee. So the validator doesn't get more than that. We could very easily in the next version change the rules of the contract to make it withdrawable by some party.
So how are the validators then incentivized to include your transactions? I missed that.
Yeah, currently they're not incentivized. They're kind of forced by the protocol. But,
cool. And my last question, for the let's say the keepers, if I'm not mistaken. Let's say if the keepers also collude with the block proposers and reveal then the transactions, so that sandwich attacks would in theory be possible. I think you briefly touched that. Can you shed some more light into what is avoiding that? Thank you.
So basically just decentralization and our security assumption. So we have hopefully the keepers just don't do it, or at least not all of the keepers. The problem with that is, like I mentioned, it's tricky to kind of prove that cryptographically, because you can make it completely in secret. So there might not be evidence. Like if they collude perfectly, then the information that they produce the key early is will never reach a party that could slash them for it. And then it's also timing dependent. So you would somehow have to prove that the key was produced at a time before a certain thing happened, and that's very difficult to do. What we can do, there's these cryptographic schemes that I'm not smart enough to explain, but basically the idea is to, I think they call it, secret sharing with snitching. So basically you, if you're one of the parties that kind of participate in collusion, you can create a proof that this collusion happened, and then you can go to a contract and kind of get rewarded if you leak that this happened. But that's that's the idea.
And I think to add to it, I think it's always also important to think about what's the worst case, right? Is that they collude and then can front run, and this is in our view like a fallback to how it's currently, right? Yeah. So I think in general we're sort of decreasing trust assumptions from just one party to this threshold trust assumption on the keeper set.
My question's more on the validator side. I probably missed something because when there's a decryption of these transactions and the block builder, which in Gnosis chain there's no specialized builder, so it's the same as the proposer. So when the builder or proposer decrypts this, so we're just trusting that they're not sophisticated enough to sandwich those decrypted transactions, and that they go directly to the builder and not to the mempool?
Yes, basically.
Okay.
So, but the thing is, so that's again the first version. But also important here is that it's observable. Like you will, notice if they start front running. Like if they don't include the transactions in the order they were supposed to, you will see that immediately. So in theory, that would make it possible to slash them in the future, for example.
Right, but there's no slashing yet.
Yes.
And if there's any slashing, and the TVL of Gnosis chain is quite small, so but at some point, like in order for an economic game to work here, the bond would need to be massive, because otherwise you're super incentivized to cheat if you can. If it's big enough, if it's bigger than whatever.
That's why ideally in the very long term it's included in the protocol. Then it's just not possible to include such a block.
And my last question, which everything was leading to this, sorry. Do forced inclusions, pre-confirmations could help somehow in this?
Maybe Fred knows about this because we've been discussing a lot about it.
Yeah, well, I was discussing it with Fred, so then we're at the same level. Okay, cool.
Basically, I'm not sure if they could help. We can definitely reuse a lot of the infrastructure that is built for this. But the pre-confirmations themselves, I don't think they like increase security. So basically what we could replace with, if we have pre-confirmations, we can replace with the sequencer contract. So basically, like we talked a little bit about commit and reveal in the beginning. So you kind of commit first to your transaction, and then it gets revealed, and the validator commits to executing transaction. And this happens conceptually right now implicitly. So the validator commits to including all transactions that end up in the sequencer contract. But they could also commit explicitly. So whenever they get an encrypted transaction, they could send a signed receipt, basically, that they will include it. But I don't think this will change like the fundamental security properties of the protocol.
All right, any other questions? I guess not. Well, thanks for joining, thanks for listening, and